Welcome to another deep dive. Looks
Yeah.
like you've sent us a whole bunch of stuff about algebraic expressions. So today we're going to try to pick out like the important parts, the interesting parts, and connect the dots for you. So you come away from this feeling like you've learned something without, being overloaded.
Yeah, it's a great collection of sources. You've got definitions and examples of addition and subtraction and multiplication.
Right.
And even though that might sound kind of basic, get ready for some pretty cool insights about how these basic operations actually lead to some really interesting ideas and applications. It's not as dry as it sounds, I promise.
So, okay, what exactly are algebraic expressions? I see here you've got things like, x plus 3 and 2y5, 3 by 2, 4 by 5 plus 7. What's the main idea we should be thinking about when we see these?
Okay, well the basic idea is that they're a way to represent quantities where maybe you don't know the exact value yet, or the value can change, right? And that's where the variables come in, the x's and the y's and so on. So you've got these variables, and you combine them with constants. Those are the fixed numbers, like the 3 or the Manischee 5, and you use mathematical operations to put it all together.
Mhm.
And the cool thing is that, these expressions can represent like a whole bunch of different numerical values depending on what the variables actually stand for. Like it's kind of like a flexible recipe where, you've got some ingredients, but you're not sure exactly how much of each one you're going to use yet.
I like that. That's a good way to put it.
Yeah.
So when we start combining these expressions, like through addition, we run into this idea of like terms, right?
Huh.
And I see here an example, 7 by 2, 4x plus 5, and you're adding that to 9 by 10. And the result is 7 by 2 plus 5 by 5.
Yeah.
So what's the underlying rule that makes this work the way it does?
Yeah, the key idea with adding algebraic expressions is that you can only combine, the parts that are really alike, those like terms, and that means they got to have the same variable, and that variable has to be raised to the same power. So, like in your example, the 7 by 2, well, there's no other term with by 2 in the second expression, so it just stays the same, right?
Right.
But the negative 4x and the plus 9x, they both have just plain x to the first power, so you combine those. And you combine them by dealing with the numbers in front, the coefficients. So negative 4 and plus 9, that gives you the plus 5x.
I see.
And same idea with the constants, the plain numbers, plus 5 and negative 10, those combine to give you negative 5. So
Yeah.
it's all about kind of like sorting and then combining what actually goes together, you know?
Yeah, yeah. Like you said, like with a recipe, you can't just throw everything in together. You got to think about, which ingredients will actually mix nicely. And
Right.
and there's an example here with even more terms, and I'm looking at it now. It's like, wow, this could get really confusing if you're not careful.
Oh, yeah.
It says we're adding 7 to x plus 5yz 3zx. That's the first one. Then we're adding 4yz plus 9z by 4y. That's the second one. And then the third expression is 9s 3yz plus 5 by 2 by psi. There's a lot to keep track of.
Absolutely. And that's where being systematic, really helps. And the solution here shows, how valuable it is to line up those like terms,
Yeah,
maybe even write them one below the other so you can really see what's going on.
right, right.
And it's a good reminder that, even though x's or z's might look different at first glance, they're actually the same term because multiplication, the order doesn't matter.
Hmm.
But the terms that don't have a mash, like the negative 4y and the plus 5x, those just get carried down into the final sum. So you end up with 5 by psi plus 9y's plus 3zx plus 5 by 4y.
Right. It's like algebraic tidiness. I like that.
Exactly.
Okay, so addition is about combining like with like. Now, what about subtraction?
Mm-hmm.
The materials here mention thinking about it as adding the additive inverse.
Mm-hmm.
Can you unpack that for us? Like, there's this example here, subtracting 5 by 2 4y2 plus 6y3 from 7 by 2 4 by psi plus 8y2 plus 5 by 3y.
Right. Well, this is a neat little trick that can really help you keep things straight and avoid those sign errors that, we all make sometimes.
Yeah, for sure.
Instead of thinking of it as like taking away, you can think of it as adding the opposite. So instead of subtracting 5 by 2, 4y2 plus 6y3, you're adding negative y 5 by 2 plus 4y2, 6y plus 3. You see, you just flip the sign of each term in the expression you're subtracting.
Yeah.
And once you've done that, then you can just, go ahead and add like you normally would, lining up those like terms.
Right, okay.
And the sources show you the result here. It's 2 by 2, 4y psi plus 12y2 plus 5 by 9y plus 3.
So it's like flipping a switch on all the signs, and then you're just back to adding. That's really helpful. Okay, so we've covered addition and subtraction. Now let's move on to multiplication.
Okay.
This is where it feels like things get really interesting because it connects to so many different things.
Yeah, you're right. It's it's fascinating how this seemingly abstract idea of multiplying these expressions actually reflects all sorts of real-world situations, like how quantities combine and change. And your material has some great examples.
Yes, it does.
Like the one with the dot pattern, right? If you have, say, m rows of dots and n columns, well, the total number of dots is MAN. But then if you add, say, 2 more rows and 3 more columns, you get m plus 2, m plus 3.
I see, I see.
And you can almost picture it, how it's growing. That's what the algebra is capturing, not just the numbers, but the relationship between them.
Yeah, it makes it so much more visual. And then we have like Amina's rectangle, where the area LAB, length times the breadth, it becomes L plus 5 AB3 if you change the dimensions.
Right.
And Sarita's bananas, remember that one? The cost, PEZ,
Yeah.
becomes P2 A4 if the price and the quantity change.
Exactly. So
Yeah.
you see, these aren't just abstract symbols, they're actually representing real changes, like in area, cost, all these practical things. It's like the algebra becomes tangible.
Yeah, it makes it so much more real, doesn't it?
Absolutely. And the text even mentions volume as another application. And then there's that try these challenge, asking about speed and time or simple interest.
Right.
It's really pushing you to think beyond just those specific examples and see how widely applicable this idea of multiplication is.
So the first thing it looks like we do is multiply monomials. And monomials are expressions with just one term, right?
Exactly. One term.
Okay, so when we multiply something like, x by 3y or 5x by another 3y, what are the fundamental rules to remember?
The core idea is actually very straightforward. You just multiply the number parts, the coefficients, together,
Yeah.
and then you multiply the variable parts together. So x times 3y just becomes 3xi. And with 5x times 3y, you do 5 times 3, which is 15, and x times y, which is xy. So you get 15 bly.
Okay.
But there's a really important thing to remember here, and that's the signs.
Right.
When you multiply 5x by negative 3y, well, a positive times a negative gives you a negative. So the result is actually negative 15 bly. Got to keep track of those signs.
Absolutely, yeah. Signs can trip you up if you're not careful.
Yeah.
Now, we also have examples here like 5x by 4 by 2 equals 20 by 3. So, what's a key thing to understand about how those variables combine?
Yeah, so here we have the rules of exponents coming in, right? When you're multiplying and you have the same base, in this case it's x, then you just add the exponents together.
I see.
And remember, if there's no exponent written, it's like there's an invisible 1 there, so x is really by 1. So by 1 times by 2 gives you x to the power of 1 plus 2, which is by 3. The numbers in front, the 5 and the 4, you just multiply those as usual to get 20. And the same logic applies when you've got multiple variables, like in 5x minus 4 by yz equals 20 by 2 yz's. The exponents of x, which are both 1, are added to give you by 2, and then you have the y and the z, each with an implied exponent of 1.
Okay, so what happens when we multiply 3 or more monomials together? The sources show 2xx, 5y, 5 a's, 7z equals 70 guys a's, and 4 by thighs, 5 by 2y2, 6 by 3y3 equals 120 by 6y6. What's the process there?
It's the same principle, really. You can just, think of it as multiplying in steps. So for the 2x times 5y 7z, you could first do 2x times 5y. And by the 7z, you could first do 2x times 5y, which gives you 10y. And then you multiply that by 7z, and you get 70 guys and my's. And actually, the order in which you multiply them doesn't matter. You can rearrange them however you like, and you'll get the same result. That's because of those properties of multiplication, commutative and associative. They let you move things around.
Right.
And for the more complicated one, 5 by 2y2, 6 by 3y3, you multiply all the coefficients together. 4 times 5 times 6, that's 120.
Okay.
And then for each variable, you add up all the exponents. So for x, it's 1 plus 2 plus 3, which is 6. And for y, it's also 1 plus 2 plus 3, so that's 6 as well. And that gives you 120 by 6y6.
I see. And then there are these examples about, finding the area of a rectangle and the volume of a rectangular box.
Right.
Like a rectangle with length 3x and breadth 5y, the area is 15y. And a box with dimensions 2x, 3y, and 5 senses, the volume is 30 abscess iz. So the pretty direct application of multiplying those single-term expressions.
Exactly. Those examples are, they're like examples 3 and 4 in the material you sent.
Yeah.
They show how this monomial multiplication just naturally pops up when you're dealing with geometric measurements that are represented algebraically.
Okay, let's move on to multiplying a monomial by a polynomial. And the source material kindly reminds us what binomials and trinomials are.
Right, 2 terms and 3 terms.
Exactly. And the big idea here seems to be the distributive law.
Yeah.
Can you explain how that works, maybe with an example like 3xx, 5y plus 2?
Yeah, the distributive law, that's a really important one in algebra.
Okay.
What it says is, basically, if you have a term multiplied by a sum or a difference inside parentheses, you can multiply that term by each part of the sum or difference individually.
Okay.
So for 3x, 5y plus 2, we distribute that 3x to both the 5y and the 2. So we calculate 3xx 5y, which is 15y, and then we calculate 3xx2, which is 6x. And the final answer is just those two products added together, 15 minus I plus 6x. And this idea of distribution, it's not just limited to algebra. Like, think about regular numbers. Like, if you're doing 7 by 106, that's the same as 7 by 100 plus 6, right?
Right.
You're distributing that 7. So it's a principle that, you probably use already in a numerical context.
Yeah, that's true. And it works the same way even if you have negative signs like -x, -y plus 2 plus 15 by y 6x.
Yeah.
Or if you have multiple variables like 5 by y, y2 plus 3 equals 5 by y3 plus 15 by y.
Exactly. You just take that term outside the parentheses and you multiply it by each term inside. And the material points out that because of the commutative property, the order doesn't really matter. So 5y plus 2, egg 3x, that'll give you the same result as 3xi plus 2. And when you extend this to multiplying a monomial by a trinomial like 3pa, 4p2 plus 5p plus 7, it's the same idea. Just distribute that 3p to all three terms inside, 3pa, 4p2 plus 3pa, 5p plus 3pa, 7. And that simplifies to 12p3 plus 15p2 plus 21p.
So then the material goes on to these examples where you first simplify expressions using this monomial multiplication, and then you plug in actual numbers for the variables, like
Correct.
example 5 with x by 3 plus 2,
Right.
and 3y, 2y7, 3y4, 63. It seems like it's often easier to simplify first before you start plugging the numbers, right?
Oh, yeah, absolutely. Simplifying first can often make the calculations much, much easier, and you're less likely to make mistakes. And then example 6 takes it a step further. It has you add expressions after you've done the monomial multiplication.
Right.
Like adding 5 meter, 3 meters, and 6 meter and 13 meters. So you first distribute that 5 meters, you get 15 meter, 5 meter 2, and then you combine like terms with that second expression.
I see. And then there's example 7, which is similar but with subtraction, right? Like subtracting 3pq from 2pqp plus q.
Yeah, you're right. And again, the first step is to do the monomial multiplication in both expressions, and then you can subtract, remembering to add the additive inverse like we talked about before.
Right. So these examples are really good for like getting comfortable with the order of operations and just how all these rules, multiplication, addition, subtraction, they all fit together when you're working with these expressions.
Absolutely.
Okay, we've covered multiplying single terms by single terms by multiple terms. So now we're at multiplying polynomials by polynomials. Let's start with multiplying a binomial by another binomial, like
Yeah.
by 2x plus 3. What's the general approach here?
Okay, so the key here is that each term in the first binomial has to be multiplied by each term in the second binomial. It's kind of like a double distributive law,
Okay.
So with by 4x, 2x plus 3, you would do x by 2x, then x is 3, then x is 4, it's 2x, and finally mooring x 4x. That gives you 2 by 2 plus 3 by 8 by 12. And often you'll find that you have like terms that you can combine, and in this case, that's the plus 3x, and the next is 8x.
Right.
So you combine those, and your final simplified answer is 2 by 2, 5 by 12.
And example 8 also gives us xy, 3x plus 5y,
Yeah.
which follows the same pattern, right?
Yeah.
Multiply each term of the first by each term of the second, combine like terms.
Exactly. You get 3 by 2 plus 5 by 3 by 3 by 5 by 2. The middle terms plus 5y's by anarchy and negative 3y's combine to give you plus 2 by y, so you end up with 3 by 2 plus 2 by y, 5 by 2.
And example 9 shows what happens when the binomials have different variables, like a plus 7, a, b, 5. You multiply everything out and you get ab 5a plus 7b, 35. But there are no like terms to combine in this case. That's your final answer.
Right. Sometimes when you multiply polynomials, you won't have any like terms to combine.
Okay.
And example 9 also has an example with higher powers, a2 plus 2b2, x, 5a3b. Multiplying that out gives you 5a3, 3b2 plus 10ab2, 6b3, and again, there are no like terms to combine.
I see. So sometimes the expanded form, that's the simplest form.
That's right.
Okay. Finally, we have multiplying a binomial by a trinomial, example 10, a plus b, a 2a3b plus c, 2a3bc. This looks like it would result in even more terms initially.
Yes. When you have a binomial times a trinomial, you could end up with 2 times 3, so that's 6 terms, before you start simplifying. And again, it's the distributive law. You have to make sure that each term in the binomial multiplies each term in the trinomial. So in example 10, you multiply a plus b by 2a 3b plus c, and you get 2a2 3ab plus ac plus 2ab 3b2 plus bc. And then you have to subtract the product of 2a, 3b, and c, which is 2ac, 3bc. And remember, when you're subtracting, you got to distribute that minus sign. So it becomes minus 2ac plus 3dc. Then you combine all the like terms, and that leads to the simplified expression, 2a2 abe 3b2ac plus 4bc.
Wow. Okay, so we really have gone deep into this world of algebraic expressions, starting with the definition and then adding, subtracting, multiplying them in all sorts of combinations. It's actually really fascinating to see how these fundamental rules build on each other and allow us to manipulate these symbolic representations of quantities and relationships.
Absolutely. And if you think back to those real world scenarios we talked about at the beginning, like the changing area of a rectangle or the cost of those bananas, you can see how understanding algebraic multiplication gives you a way to analyze how those quantities are affected by changes in the variables. It's like a framework for modeling those situations and making predictions, which is, something you can't really do with just plain arithmetic.
So, having heard all of this, I want you to think about this. Algebraic expressions, they're not just these abstract symbols on a page. They're a language for describing how things change, how they grow, how they relate to each other. What other areas of your life, maybe, fields of study, hobbies, whatever, what other areas do you think you could describe or understand better using this algebraic way of thinking?
Yeah.
It's really quite remarkable how this system, with just these basic variables and operations, it can be so powerful for representing the world around us. Yeah, and what we've done today is really just the beginning. Algebra goes much deeper than this.
Oh, yeah.
There's a whole world of more intricate and powerful tools out there. And if anything we've talked about today has sparked your curiosity, or if you have more questions as you continue learning, don't hesitate to reach out. We're always ready for another deep dive.
Yeah.